Hello and welcome to another Physical Sciences 3 lecture. We're looking at electrical circuits and specifically series and parallel connections today. So we have two ways of connecting circuits in an electric circuit, or components in an electric circuit, I should say. Here we have two resistors, so R1 and R2, and they are in series. And then similarly we have two resistors here, but they are in parallel. Okay, so in a series connection, all the current passes through both components, and so that means that this current is the same. Okay, so across there, the current is the same. Whereas with a parallel circuit, we have a current in, which is called the total circuit of the current. And then we have one branch coming off here, and we call that I1. And then we have another branch coming this way, which we call I2. So then I1 goes through the first resistor and I2 goes through the second resistor. And what happens here is we get the current is equal to I1 plus I2. Oops, I2, that doesn't look very nice. I2. So before and after the current passes through the resistors are the same, but it will go through different branches of the parallel circuits depending on how powerful or how much resistance each resistor has. So a current will choose the path of least resistance. So if there's more resistance in one branch, then it will prefer to go through the other. The other thing we have to talk about is voltage. So if we measure a voltage across here, we call that one V1 and V2. So then the total voltage across here, V total, would be equal to V1 plus V2. It's slightly different for a parallel circuit. If you take the voltage across either of the two resistors, okay, see how like they both share the same kind of point. So V total is equal to V1, which is also equal to V2. So the voltage is the same across both resistors there. Okay, and it summarizes that in those notes for you. So you want to have an understanding of series and parallel connections when we're talking about ammeters and voltmeters. So an ammeter measures the amps, which is the current, measures current. And we can put in brackets amps there, measures the amps. And a voltmeter, probably unsurprisingly, measures the voltage. And that's in volts. Okay, the key thing is how they're connected. So this one is connected in series. It says in our notes there, and these ones are connected in parallel. So those ones are connected in parallel there. Okay, so, and like it says here, measures amps, measures voltage, like I said. Oh, the other key thing is an ammeter has low resistance. Okay, so I say that R goes to 0, and that's so that it doesn't impede the flow or the current. Whereas you want the opposite case for a voltmeter. You want that to go to infinity because then all the current will want to pass through here. The current will go past there, and so the current down here, I, is basically equal to 0. You don't want any current going through the voltmeter. You just want to be able to measure the voltage drop across that. So you don't want the voltmeter to actually affect the circuit. Same with the ammeter. You can draw them both in on the same circuit. So if we have this circuit here, which has a power supply and a resistor, we've done the ammeter and we've put that in series with the two, and the voltmeter is in parallel with the component we want to measure. Okay. So whatever component you want to measure in a circuit, if you want to see what the voltage drop is across that component, then you measure in parallel with that component. We have a bit more on components in series now, so consider two resistors connected in series here. Like we were saying before, the voltage total is equal to the sum of V1 and V2. So just see we've got this is in parallel with R1, and this is in parallel with R2. Okay, so you got those two voltages there, and the total voltage is equal to the voltage supplied to the circuit by the battery, and it's equal to V1 plus V2. So for the entire circuit, Ohm's law holds. So this is Ohm's law, and Ohm's law also holds for each resistor as well. So V equals IR across each resistor, and then if you substitute those back into our equation up here, V total is V1 plus V2. Okay, you end up getting this this equation here, and basically the important thing is if we want to calculate the resistance for resistors in series, we just add them all together. So it's pretty simple. So if we have a circuit here, which we have two resistors in series, so we have this one is 220 ohms, and then we have this one here, which is 470 ohms, then that is equivalent to one resistor of 220 plus 470, which is equal to 690 ohms. So pretty straightforward for circuits in series or resistors in series. Components in parallel are slightly different. So like we had here before, we have a current going in, and that is I total, so that's equal to I total there. And then it branches off into I1 going down here, and I2 going down there, and we can measure them by putting ammeters in series. So those ammeters are in series there, and the total current, so the current before and after the branching, is equal to I1 plus I2. And again, Ohm's law holds again for this total circuit, and also across each component as well. And if we go through the process, we can work out that the total resistance is equal to here, but the note down there says this is only for two resistors. If we had more resistors, you could go at this point R3 plus R4 plus however many. But as we go through, as we try to simplify that, it's going to become much more complicated, a much more complicated equation. Okay, and I encourage you to do the next step and just try and rearrange them. And it does get more complicated more quickly, or you can look that up. But if we have two, and that's all we're going to be concentrating in this course, we don't have to worry about when we have two. And we'll have a look at the example for that. We just want to do an equivalent circuit. So this time we have the same resistors, but in parallel. So this time it's 220 down here. We can draw that there, and then we have another one in parallel here. Oops. Make sure your circuit is connected. This is 470. So this time the R total is going to be equal to 220 times 470 over 220 plus 470. And when we put that into our calculator, we're going to be with 220 times 470 divided by 690. So it's 100, ends up being 150 ohms. 150 ohms, and so the equivalent circuit is 150. And it's useful because we can then easily calculate what this I total would be, and that I total is equal to this I total and that I total. Okay, so we can work out what the current is easily if we know that one. Just quickly on ohmic or non-ohmic, what we have here is a graph of an ohmic conductor. And the key is if you take the gradient, if you find the gradient, just remembering we have rise there and run along there. In this case, the rise will be equal to I and the run is equal to V. So if we take 1 over the gradient, that might be a bit of a different concept for you, but if you find the gradient and divide 1 by that, this is equal to, instead of rise over run, it's equal to run over rise, which is equal to V over I, and that's equal to the resistance. So if the R is constant, we have an ohmic conductor. It follows Ohm's law. And a non-ohmic conductor is simply one that does not follow Ohm's law, which means that the gradient is not constant for these graphs here. Gradient is not constant, so if you get these ones, then we have a non-ohmic conductor. Something like a light emitting diode, a light bulb, considered non-ohmic conductors. Okay, just a word of caution that sometimes that you can get segments of a non-ohmic component, which would be ohmic for a certain range, but you'll see them in examples as they come up. And we cover power, the electrical power, in the next video.